just wait for 2 seconds because we are quickly approaching the limit. 63. 64. Right. So we can start right now. Ladies and gentlemen, dear participants, a warm welcome to our HOLISHIP public workshop. We are very happy to be able to present HOLISHIP during such difficult times in a modern format using video conferencing tools, and have the opportunity to stage this event. We are also very proud to give you a representative overview of the successful work that has been accomplished in the project. And all this was possible through a considerable grant that we received from the European Commission in the context of the Horizon 2020 framework, specifically the research program. HOLISHIP puts advanced ship and other maritime assets design technologies to use in a novel and advanced design synthesis context. Today we will hear 5 presentations elaborating the concept of the new design thinking. That's by Apostolos Papanikolaou. The design platforms developed and used in the project by Stefan Harries, and then we have 3 application cases that were run by HOLISHIP users. The first one being a complex power system configuration for an OSV vessel, which is presented by Paulo Macedo and Sverre Torben from Kongsberg. The second application case that is being presented is the concept design for an advanced RoPAX ferry by Mermiris Tritec. And the third one is the intelligent general arrangement for double-ended ferry example presented by Markus Jokinen from Elomatic. We are aware that this is a comprehensive and slightly demanding program for a web-based meeting, which goes a little beyond your typical webinar that we all used to by now since March this year. We try to keep all the presentations as concise as possible and give a quick start. We anticipate that the whole event will last about two and a half hours. We should be ready by 12:30. But then HOLISHIP, you have to bear in mind, is a large project, and there's much to be told about the developments and the individual items and tools that we developed, and which will clearly change the face of ship design in the coming years. Just a little bit of housekeeping for today's presentation. We will record the presentations, and they will be available after the meeting. You can access them through the link that you received when registering. We will have a question and answer session at the end of each presentation. That necessarily needs to be short, but we expect to allow at least 5 minutes for questions and answers after each presentation. You can use the question function in the panel. That will look approximately like the little image here on the right-hand side of the slide. And then we will have a small questionnaire at the end of the workshop. When you leave, this will pop up, and you will be asked 5 or 6 questions, I believe, 8 are, and excuse me, and that will take you less than 3 minutes to complete. That's it from me for the start, and I would like to ask Mattia to change the controls over to Apostolos Papanikolaou, who will give the first presentation.
So thank you, Mattia. Ladies and gentlemen, it is my pleasure and great honor to present you on behalf of the HOLISHIP Consortium my presentation that will be dealing with an overview of the HOLISHIP project, the philosophy behind this project. In that respect, I need to cite Aristoteles in his Metaphysics, who introduced the concept of holism, namely that the whole is more than the sum of the parts, that is inherent to nonlinear systems like ship design is. And of course, also, I should also say that in practice, we have proven that the HOLISHIP approach is workable, and this is demonstrated by 9 applications and demonstrators that have been worked out by teams of the HOLISHIP consortium. The HOLISHIP project is a 4-year project that ends at the end of this month, and it is carried out by representatives of the European maritime industry and scientific community. Actually, 40 representatives were initially in this project. Maybe now they are 37, 38. In any case, this project is coordinated by HSVA Hamburg, and project manager is Dr. Jochen Marzi, who is moderating today's event. These are the partners of HOLISHIP. Actually, they are representing whole Europe from north to south, west to the east, and most prominent maritime industry representatives, and actually also coming from research and academic community. What is the HOLISHIP approach? Actually, it refers to the parametric, multi-objective, and multidisciplinary optimization of ships and maritime products in general for life cycle. The HOLISHIP approach includes virtual reality product modeling and virtual prototyping, and enables also multi-site cloud working. Some references to the project: a publication that I had 10 years ago about the holistic approach to ship design and ship design optimization, and then a paper that will be published maybe early next year that was already accepted at the Journal of Ship Research, that is co-authored by representatives of our project, and is about development of tools and applications. And last but not least, we have already published a book about HOLISHIP, namely the development of tools, volume 1, that you see there in January 2019. And the second volume will appear in early 2021, showing the application cases. Now, let me compare the traditional approach to ship design with a design synthesis that we are promoting in HOLISHIP. The traditional design spiral that was introduced 60 years ago by Professor Evans considers actually the design process as a spiral. The various steps of ship design are here on the spikes of this spiral. And very important here is that going from the concept design, that is the first loop on this spiral, to the detailed design, the effort is increasing by a factor between 12 and 17. Of course, these, regarding the absolute numbers, these are values that are drastically reduced nowadays, and even more by the HOLISHIP project, as I will explain later on. The HOLISHIP approach to ship design is based on a synthesis modeling of the various disciplines that contribute to ship design, and they are all processed in parallel, not in serial way. This is a significant change in the design process, and of course, in order to do that parallel processing, you need heavily to use computer software and hardware. Ship design is inherently related to optimization. I like here to call a paper by Professor Novaki, Bruce, and Schrift 50 years ago, namely a paper about the tanker preliminary design optimization problem with constraint, showing the ship design process as a decision process in which design variables and parameters are assessed on the basis of merit functions and keeping certain constraints in mind. Now, here was later on elaborated by me and a variety of my students, and led to this kind of approach a multi-objective optimization in which the variation of the design is enabled by parametric models for ship's geometry and outfitting. This refers to the halvo, the arrangement of spaces, arrangement of outfitting, structural arrangements, and maybe other issues of ship design that may be parameterized. The optimization criteria are manifold, and they go from performance and efficiency indicators, minimization of environmental impact, minimization of building and operational cost, and maximization of profit and other economic values that may be formulated in mathematics and solved in this design optimization problem. Constraints are coming from regulations set by society, by market demand and supply, the cost of major materials like steel and fuel, and price for workmanship and other that may be dependent on the specific ship type. Our approach to this complicated problem is a combined bottom-up and top-down approach. We started actually bottom-up by having tools available that were applied in a variety of application cases. On the other side, at the beginning of the project, we postulated two design platforms in which the tools that came from the application cases were integrated. And these two platforms are the cases platform that is developed by Friendship Systems, and HOLISHIP RCE that is developed by the Deutsche Luftraumfahrt, a research institute dealing with aviation industry. This combined approach enabled us to set up a system for generating designs that are assessed, and then finally we get also from experience some feedback in order to improve this kind of loop. And finally, the application of this approach to a variety of demonstrators prove that this concept is working. Here an example of the design synthesis for a RoPAX design on the base of the cases platform. This will be also elaborated in the next presentation by Dr. Harries. In any case, you see here a variety of tools that refer to properties of the design, and they are evaluated by certain software tools that are available to the partnership. And we may also use external software like the professional software platform NAPA for doing the inter-academic stability of the ship. All this contribute to the design that is to a great extent automated by computerized macros and other refinements undertaken by the team. On the other side, the RCE platform of DLR was used for the simulation of ship maneuvering of a cargo ship that was demonstrated on the bridge simulator of Marine. In this platform, we have the integration of tools coming from Marine, TNO, and DMC on this platform, and the results of this integration are represented by response surfaces that fit the bridge simulator of Marine, and then some navigation scenarios can run by a captain to see the difference between alternative rudder arrangements and the effect on the maneuverability. Last but not least, we could demonstrate that through cloud communication of the HOLISHIP platforms, namely of cases and RCE, we could have a multi-site working, namely partners sitting in Hackenigen from Marine, Potsdam, Friendship Systems. In Hamburg is DLR with the RCE platform, and in Athens we had some application software running on a certain scenario. The 9 application cases, part of which will be presented in the following, refer to the concept design, contract design, and virtual testing for a variety of ships, variety of ship types. And you see here the extent of these demonstrations. Actually, the demonstrators are more than 9, because in some of these cases we have a variety of alternatives and alternative demonstrations of the visibility of the concept. Now, I come to a comparison between the conventional and the HOLISHIP approach in order to show you the difference. I have a variety of points on which I compare the two approaches. On the concept design, the conventional approach is actually empirical and highly depends on the experience of the designer, developing maybe 2-3 variants of a baseline design and intuitively selecting the most promising out of them. In HOLISHIP, we have the automated parametric generation of hundreds of designs. I call them digital siblings, not twins. The digital siblings are actually parametric models here of the hull form that is parametrically changed and is considered in the design process. On the base of this parametric variation of the hull form and the whole design, we may proceed with a global optimization for determining the main dimensions of the vessel in question. Here is a RoPAX that we consider for 2 parameters, the propulsion power design draft and the deadweight capacity at different drafts. And you see here a variety of points, all of them representing feasible designs. We have not drawn here the unfeasible designs that do not pass the constraints. And a clear Pareto front here with 3 designs, 3 promising designs that were followed for more detailed investigations. Note that here the baseline design is an unfeasible design, practically because of the change of stability regulations. This vessel could not pass the most recent regulations and needed to be redesigned. Regarding the preliminary contract design, again, we differentiate between the 2 approaches, the sequential processing of design steps and the parallel processing of the design steps. In this case, as I have shown earlier, we adopt a multi-objective and multidisciplinary optimization of several hundreds of design variants. And even we can go now at these steps at some local optimization of the hull form, as demonstrated here for a catamaran hull form, for which we optimize the transom stern for high efficiency. And in fact, we could prove that this efficiency is superior compared to what we have known until now. With respect to the accuracy of the calculations methods involved, whereas in the conventional approach, the accuracy of the methods used is low at the concept design, in the HOLISHIP approach, the accuracy is high at any desired level because we use the surrogate models approach by which intensive calculation tasks are actually pre-calculated, and formulation of the surrogate models leads to some very quick assessment of the variance that we have in mind. Regarding the design lead time and the person month efforts, these are a little bit touched at the beginning of this presentation. But assuming the availability of suitable parametric models, the time that we can save, I think, is in a factor more than 5 compared to the conventional approach. That is also computer supported, I must say. It is not the approach I have shown 60 years ago. With respect to what we have today, by a conventional approach that is supported by computer-aided tools. On the other side, we have to admit that in order to achieve this lead time, short lead time, we need to have parametric models in hand. Now, this is something not trivial, but I think it is something that will form the future of naval architecture, namely not to have simple drawings of baseline design and calculatory sheets, but just develop parametric models for the ships that we like also in the future to redesign. This is some effort that takes some time, depends here on the modeler's experience, and I think it is a very important task for future naval architects to be trained to be able to do this. Regarding the cost, in the HOLISHIP approach, we have an early assessment of the effect of hundreds of design variants on cost, both on CAPEX and OPEX. Whereas in the conventional approach, this is done to a limited extent and surely not for all the variants that we are doing in the HOLISHIP approach. The quality of design on one side highly depends on the designers and yards experience. And for sure, there are very good designers and yards in that respect. On the other side, in the HOLISHIP approach, we have a superior quality thanks to the systematic optimization and selection of the best variants out of hundreds of designs. And this is ensured by the workflows that we have programmed and also the design tools that we are using. In that respect, actually here the contribution of experts is less necessary than in the conventional approach. Regarding the safety of the ship and of the marine environment, a clear go-ahead for the HOLISHIP approach that has been also demonstrated in previous projects. We have a risk-based design here with quantifiable risk and quantified level of safety, whereas the conventional approach is that we have a rules-based design with undefined safety level. Regarding the energy efficiency, in the HOLISHIP approach, we look at the consumption of all energy contributors, not just the machinery propeller interaction, and this already at early design stage by proper tools that have been integrated in our design platforms. The life cycle performance assessment refers in the HOLISHIP approach both to economics and environmental impact. That means the emissions on the environment. Innovations in ship design actually only enabled by an approach that is simulation-based, because in the lack of baseline design, we cannot build upon it in order to generate an innovative ship design. Our software platforms are flexible and with simple communication protocols, something very important. We have already integrated a large list of software tools that will be also shown later by Dr. Harries. We may integrate also professional naval architectural software platforms, not integrate, but communicate with them and use them as necessary for some design tasks where other tools are lacking in our list. Design workflow procedures. Our approach enables the coding of design workflow by macros, and this has been demonstrated already in a variety of application cases, and not only those shown here in the frame of the HOLISHIP project. Regarding distributed working and cloud communication, I think it is something that in ship design is not known, or maybe in limited extent, whereas we have demonstrated that in the HOLISHIP project through the communication between RC and the cases platforms. The virtual prototyping is also something new in ship design. It was here demonstrated by the simulation maneuverability of a ship with alternative radars on Marine's bridge simulator. And finally, the acceptance by the industry. This is something that I have to say, of course, the conventional approach, trivially, it is accepted by the industry because it is following this. On the other side, at present, our approach is limited to the HOLISHIP partners and knowledgeable academia. The acceptance is growing, as I can see, at least at a scientific level, judging from research works of people that are taking reference to this. On the other side, I think it is a matter of future education of naval architects to accept this approach, train properly the engineers in order to follow this approach in the future. I conclude with a summary of what we have achieved. We have achieved a design synthesis integration of software tools in a combined top-down and bottom-up approach. We have conducted parametric multi-objective design optimization by the cases platform, also by the RC platform. We have shown the flexibility of combination of tools as needed for specific design tasks. Our synthesis models are steadily growing in terms of content and refer to more application cases. We have replaced resource-intensive simulations with surrogate models, and this was demonstrated by many teams within the HOLISHIP project. We have demonstrated the VR modeling via the RC platform and also distributed working. And of course, we have proven that the concept is working in a variety of application cases. Closing, I need to acknowledge the contribution of all partners, representatives of HOLISHIP, because it is a joint effort, maybe of some 100 engineers and scientists who worked in the HOLISHIP project in the last 4 years. The work was funded by the European Community in the term of Horizon 2020. And for this, I'd like to thank deeply both the partners and the European Community for this support. Thanks very much.
Thank you, Apostolos, for this presentation. I think we do have a few minutes for questions, although I noticed that there is no input from the participants in the question panel. I would try to motivate you to ask questions in writing, and we will of course try to answer them after each presentation. I admit that it is probably a little difficult to start with questions regarding the previous presentation, because it is extremely complex, and on one hand, and on the other hand, as we believe, the concept, the idea of the holistic model, the synthesis approach to ship design should be so evident that more or less it goes without saying. And if you follow recent developments, you will notice that also the big players in the software players in the design fields have adopted the idea, and you will find similar approaches and concepts also in their design systems. In that respect, we totally believe that we are on the right way, and that whatever HOLISHIP has produced during the past 4 years will have a very big future. I can't see any specific question at the moment. Therefore, I would like to give over the controls to Stefan Harries, who is going to give us an introduction to. Well, wait a minute. There's something popping up in the questions. The first one asking how other universities or countries can participate in the HOLISHIP program. Is there a web-based platform? We have some research about ship hull optimization from Amin Nazimian. I'm sorry, I hope I'm not mispronouncing your name. I can probably answer this question. HOLISHIP is an EU project which is going to reach its end at the end of the year. Therefore, HOLISHIP itself will not offer any opportunity to participate. But Stefan is going to present to hint on some ideas that we have for the future in his the following presentation. Maybe that gives you an idea how future collaboration could look like. And there is another question: how important are programming skills for naval architects? That is probably something that Apostolos might refer to.
Yeah, I think I touched the subject, and I think it is very important. And especially not only that they need to know how to program, but also, as I said, the modeling of ships in the future the digital modeling of ships. It's something very important that requires both knowledge of ship design, but also you need to have IT tools in order to do that. It is not easy to say, I will put an IT man and tell him how to parameterize a ship design. This is actually impossible. Naval architects need to be trained to do that. And if they have it, a complete new world is there in order to optimize what you have parameterized. Because out of that, as I have shown, you can develop many, many siblings and assess them by methods that are well known in other disciplines. So that is the new direction that we are promoting in HOLISHIP. And as I said, I think education needs to be adapted to this. We try to contribute to this by the publication of books on this and also series of other publications in journals and so on. But it needs, of course, to be adopted also by the teachers and the industry in order to finally to succeed.
Good. Thank you very much. I'm still keeping an eye on the watch on the time. There are 2 more questions, but I believe Stefan's presentation will give an answer to them. Therefore, I would like to continue with Stefan Harries as our next presenter. Anyhow, all of the questions that you ask we do receive them, and we know, and we will give an answer to you by email, probably, most likely by email after this this little workshop. Thank you very much. So, Stefan, the floor is yours.
Thank you, Johan. Can I quickly check? Can everybody see my PowerPoint presentation?
Yes.
Yes.
Okay, perfect. All right. Good morning, everybody. I will give you further insight into HOLISHIP design platform or platforms, as we have created them in a bottom-up approach within one of the work packages. I will naturally focus on some of the aspects that have been worked on over 4 years. So forgive me for those people that are present and participated if you are not explicitly mentioned. But I try my best to give an overview how we brought together many, many tools. My name is Stefan Harries. I am one of the CEOs at Friendship Systems. And the content of my presentation is as follows. I try to elaborate a bit more on the synthesis models already introduced by Professor Papanikolaou. I'd say a few words about how we actually integrate methods and tools, how we do the data management within HOLISHIP, and how to replace very complex simulations by surrogates or surrogate models. Professor Papanikolaou already mentioned that many tools and platforms are, of course, in the market, and we have chosen to collaborate with these platforms, not to aim at replacing anything. I'll say a few words about that. And then I'll just to say briefly mention one application case a bit more in detail, the RoPAX Ferry, that was already also mentioned a little bit, to give you a more thorough understanding of how the integration works. And then I come to concluding remarks, and as Jochen pointed out, I will say a few words about where we could go beyond HOLISHIP. You see here dominoes. These are representative of tools in the market, and yeah, holds more than the sum of the parts. If you nicely combine these dominoes, you can get something better. This is the aim. So replacing the design spiral, we want to build synthesis models, and I'll show you a few synthesis models in a minute. Let us quickly take a look at how we approach the whole integration. It comes from simulation-driven design. So you basically bring various components together, and just for the sake of illustrating it, I'll show you this for the simulation-driven design in hydrodynamics, where you have geometry, grid generation, flow simulation, and then you do what we would call exploration and exploitation, part of what was formerly called formal optimization. Now, For process integration and design optimization, you need what is called a PIDO, a process integration design optimization platform. We used, not surprisingly, CASES, because CASES is from Francis Systems. It is called CASES because it stands for Computer-Aided Engineering System Empowering Simulation, and it can integrate and couple to any tool that can be run in batch mode. Basically, we use a very simple approach. There are typically input and output files if a tool can be run in batch mode, and we use those input and output files as templates to connect to CASES. And once that connection has been established, which can be done with very basic programming skills, that is a partial answer to the question just posed. You don't have to be a C++ expert or C# expert to do this. It's just really going through the templates and identifying those items that you'd like to connect, that you'd like to share. Then you tell the system where the tool is placed so that you can run it. And then once the tool is ready and has produced output files, then you just take out those data items that you are interested in and pass them back to the integration platform. This is the general idea. And that was realized within work package 7 of the HOLISHIP project. I'd like to mention the task leaders within this work package, Hochschule Bremen, National Technical University of Athens, and DNVGL, who were extremely busy and very active in bringing many tools together and supporting everyone in integration. As you can imagine, there are many tools. It's just a glimpse to give you an idea. There are, of course, even more tools that I'll show you in a minute. But let me explain quickly again how a tool is integrated specifically. You have now the general concept of using templates, and I'll show you here the integration on an abstract level for a tool, New Shallow by HSVA. It's a potential flow analysis code for calm water resistance. And what you can see here are typical inputs, input geometry, for instance, and input files. So for the geometry, you might just need a panel file. For running a tool like New Shallow, you might need a control file. When you then trigger it, you definitely get outputs, and that can be typically ASCII format, say comma separate value files, or it can be general files like PNG, VTK, NSIDE, HTML files. So the way to integrate tools is very flexible. We support within the HOLISHIP platforms the various standards, but since many tools, particularly those coming from academia, often use comma separated value files or special formats, that can also be accommodated. Okay, so the standard process when you run an optimization, when you do an exploration or an exploitation, is you identify the parameters that you'd like to modify. These are the free variables. And if you do so and integrate many tools, you of course can couple such that one tool produces data that is needed by another tool. How do we handle this? And I'll show you this in this upcoming slide here. There's data coming from tool 1, and say another tool, tool 2, might need parts of that data. And yet another tool might again need parts of tool 2 and tool 1. So what we do within the HOLISHIP integration is we hold those data items that are needed to be exchanged and that are of interest for the actual design and optimization task. Those data items that are maybe beyond what is typically needed for a designer are kept locally, are not shared through the HOLISHIP platform. Think of a New Shallow analysis. You would have a potential flow analysis of your flow field. You are probably not interested so much in every single velocity and pressure point in your flow field. So that would be kept outside the HOLISHIP platform with a reference to the file names where those data can be found later on. But you might just want to keep centrally things like resistance, sinkage, and trim, etc. The bottom-up approach that we have taken allows that data can be shared ad hoc. So if a new tool comes into play, you just couple it, and you can nicely expand data sets and keep the results as the project or the projects evolve. Now, the synthesis models, and this is not to go through the details because we will have very nice presentations in a minute, right after me, look quite different. I'll just give you a glimpse, I go back and forth. This is, for instance, the synthesis model for an offshore supply vessel, as will be given a presentation by Kongsberg. This is the synthesis model for a double-ended ferry, as will be explained in a minute by Elomatic. And this, for instance, is the synthesis model for a multi-purpose offshore vessel. You have very different tools that need to work together. So you need something in this bottom-up approach to bring it together very quickly and very flexibly. When you run the various tools, you realize that sometimes you need similar data to go into the various tools, but they are not essentially exactly the same. And this is shown here. So within the HOLISHip design platforms, we have to manage the data in a way that we convert it, we sometimes enrich it, and we post-process it. This is an illustration for this. This is a parametric model for such a hull form. It's a RoPAX vessel that we looked into. So tool one might just need a panel file where there are panels over the wetted surface and part of the freeboard. The next tool then might just need panels that are covering the wetted surface, and the panels look slightly different. This is actually for calm water resistance by New Shallow. This is for the seakeeping analysis, a potential flow seakeeping analysis by New Drift from NTUA. And then you might just do some hydrostatics, more sophisticated stuff, damage stability, input, etc., etc. So you have to enrich the data within the platform, and this is what we have achieved and that we provide. I'm not going to go through this list. I just wanted to mention a few of the tools that were integrated, so you get an appreciation that there has been a lot of work going into it. And some tools have been used in different application cases, and yet the integration could then be just used again, maybe with some additional data to be provided. I already mentioned at the start of my presentation that we would use surrogate models. Why would we do that? When we look at the standard process, you realize, of course, that some tools are rather complex. Maybe you have a RANS code where you do a viscous flow analysis, including the free surface, and maybe even the working propeller. That tool might need expert knowledge. It might need special hardware even. You definitely will need certain software licenses. And those tools might take a few hours to complete and to converge. So we said, in order to be able that a team of designers can work with these tools a bit more flexibly and a bit faster than what we do currently in a traditional approach, we replace them with surrogates. So we basically run upfront design of experiments that can be a SOBOL or Latin hypercube, for instance. Then we encapsulate the data for the designer. We can think of that as numerical series, so to say, also for reusage in different applications. And that then, of course, speeds up the whole design task when it comes to it. There are different ways to replace the data with surrogates. Classical approach is a polynomial regression, but we have provided also artificial neural networks, kriging, and other tools to wrap that up. If we go back to that RoPAX Ferry example, this is a synthesis model that Professor Apostolos Papanikolaou also showed. You see that we would replace, and this is sort of say shown here with almost black boxes, it's gray boxes. We would replace that with surrogates because a seakeeping analysis, a resistance analysis, damage stability analysis are all things that might not take hours and hours per variant, but they still need a few minutes, 10 minutes, say, on a standard PC. And then, of course, it's very much more comfortable to have them wrapped and then get results and feedback immediately when you run designs. How do surrogates look? This is a simple example from a double-ended ferry, change of resistance versus beam and length. So there's nothing extraordinary, just giving you an appreciation. And we have, of course, also made checks to see the validity of that surrogate approach. Here, for instance, on the ordinate, you would have the resistance given from the response surface versus the actual resistance computed. And you see that the data lies within the plus minus 1% error line. For added resistance in waves, this is the picture here to the right. It looks very similar with slightly larger error lines, plus minus 2.5%, which is absolutely okay when you change your hull and when you change your design at a wider scope, what you want to do early on. Collaborating platforms. As said, we are not replacing with our HOLISHIP platform or platforms everything that's already there. That would be absolutely meaningless, but there is tight collaborating mechanisms between the various platforms. I've shown here a few that we have put together. You have seen this slide already, so I can skip that. And then let's take a quick look at how tools work together. For instance, NAPA works very closely together with cases. I work done at HSV, at Hochschule Bremen, and at National Technical University of Athens. I go back to this slide. This is how it was run and set up for a double-ended ferry, where you would have the geometry and a certain data coming from the platform, from cases, going into NAPA, then a lot of macros programmed by HSV were executed, and then you would get output data for intact and damage stability. Similar for a different type of hull form. What I'd like to point out here is the flexibility of changing geometry. So for instance, if you enlarge this RoPAX ferry, for instance, you would not only get a snapping of the internals onto the outer hull form, but you, depending on the changes, would also be able to introduce additional bulkheads, change certain compartments. Cases and NAPA steel, as will be further explained by Tritec later on. Cases and Cadmatic. There's also more to be heard from Markus from Elomatic in a minute. So I don't need to get into the details here, just to mention that the approach is such that, for instance, Cadmatic gets the latest geometry, the variant we investigated, and then automatically generates the inner structure and gives weights and structure integrity data. I skipped that cases and the answers workbench that was used in all the application cases that we will not be able to present in more detail. Just to wrap it up a little bit, this is the RoPAX ferry that we looked into in work package 7. The synthesis model you have already seen. This gives you an appreciation of the parametric model. This is, in a way, a certain programming exercise, but you, again, don't need to be an expert in C++ or whatever. It's then typically a macro, or in cases, it's a feature that you would program to build up such a parametric model. That is then passed to NAPA. The geometry we would then generate automatically by means of the material researched and provided by NTUA, the inner structure, and then we run design, exploration, and come up with, so to say, very sophisticated data, because now we don't only have 2 or 3 or 4 variants, but we have many variants to choose from. This is an example where we plot, or where NTUA actually plotted, and I used that, the attained index from damage stability. It's the margin versus the required index. So on the ordinate, you basically see a measure for the safety of the vessel, while on the abscissa, there is plotted the net present value, namely the change versus the baseline that was investigated. And this is then a typical outcome from such an exercise, that you would have many, many variants to choose from that are all feasible and that make up a Pareto frontier. So you can choose deliberately and consciously your best balance between, for instance, safety and economics. As said, more data will be shown for the double-ended ferry, for the RoPAX ferry, and for the offshore supply vessel. So I will skip that. Come to my concluding remarks. Data to be generated, shared, managed, and studied are quite diverse. I think this has become clear already. We have opted to replace resource-intensive simulations with surrogate models to make life easier for the actual design team to use that data. The synthesis models are rather complex, but we managed to cope with that complexity by following a bottom-up approach. So you can bring in tools as projects evolve. You can actually replace tools with better data as it becomes available. And you can very nicely combine things. So it's not a one thing that covers everything. That's not a solution that would be good for all types of application cases that you can think of, but it's an approach and the mechanisms that we provide that the designers can work on these projects and build them up as time goes by. You would then have a lot of different parametric models to choose from and be very, very quick when you set up 2 projects. If you want to read more, of course, Apostolos already mentioned that too. We have 2 books, one already published, one to be published very soon, where everything is really explained in much more detail than what I have explained here. But I have a few more slides, so bear with me, of how could things go on further. And this is, so to say, going a bit beyond HOLISHIP. When you have lots of tools, lots of tool providers, lots of platform providers, and people that need those tools, the idea that has come up within HOLISHIP, and that has also similarly been discussed in another European project that has come to an end a short while ago, namely Shipless, the natural way forward is maybe to create marketplaces, to create a place where both customers that need tools can go to that marketplace and meet providers of tools and consultants that offer that. So similar to you going to the market and buying your cheese and bread and olives and whatnot, you would then go to a e-commerce marketplace in the web and buy your structural analysis or your damage stability analysis, or you would get a parametric model for your swath design that you are interested in, or you would ask a consultant to provide you with a bow optimization for the hull form that you have already created. These are all options that we see that we can work on in addition to what has already been put into place within the 2 projects, HOLISHIP and Shipless. Just to give you an appreciation of that, it's just a mock-up, so prices are for illustration only. Gives you an idea that you can then select tools very quickly, put it to your card. You might have, so to say, your PayPal or your MasterCard, your company's MasterCard already registered, and then, so to say, be much, much quicker than asking for an offer, maybe having to discuss quite intensively with the provider, and then a few days later being able to start. That brings me to the end of my presentation. I have a little video that I can show while there might be questions to be answered. I'd like to thank very much all partners for the hard work. As leader of Work Package 7, where we worked on the integration, I know how much time you put into this, so thank you very much for this. I also like to thank the European Union for funding HOLISHIP. Without the support, that would not have taken off. But there are two people, and they have already presented, that need special acknowledgement to me. This is Dr. Jochen Marzi from HSVA and Professor Apostolos Papanikolaou from HSVA and from NTUA. Without the two gentlemen, that project would not have started and it would not have run, and let's maybe keep the maritime term, sailed so smoothly. And of course, thank you all for your attention. And while maybe you are posing questions, I can show a little animation of how a marketplace beyond HOLISHIP would work. Thank you.
Thank you very much, Stefan, for this presentation and for the appreciation. Very much acknowledged. In the meantime, there are a few questions that have arrived. I would like to start with first my hope that one or two of the questions asked for the previous presentation from Apostolos have been more or less answered with your presentation here. The holistic approach can clearly be adopted with software currently in use by just linking, as Stefan has explained, them to our systems. Now, there are two new things which I see here. One is a question asked by Henrik Dankowski: how is completeness of all constraints and the influence of the change of design parameters controlled, checked? Is the robustness and correctness of the coupled tools checked by the platform? That is something I would like to transfer to Stefan.
Yeah.
Can I repeat this, or?
Yeah. Shall I already answer? Yeah. So the constraints, you can actually pose constraints, both equality and inequality constraints in the platform. Of course, as the designer or the design team, you have to ensure that the right constraints are put into the platform, so there are no mechanisms to automatically check for constraints. But the flexibility is that you can use any data that you provide through the tools that you use and that are made available to the platform for checking constraints. And what is in addition, once you have set up those constraints, they will be checked diligently throughout the entire design space. So whenever you create a variant, it will be checked for these constraints so that you would immediately see, is that a feasible design or is it an infeasible design?
Okay, thank you. And there's another question asked by Daniel Baccarolo. Have you analyzed how sensible is the final result of the optimization to the precision level of complexity of each of the components, for instance, stability, resistance, structural, and so on? Are surrogate models enough for all the design stages?
Yeah.
I think you partly gave an answer to that already.
Yeah, maybe I'll start with the second part of the question first. Since you can replace the surrogates at any point with the true simulation code, you can decide on your own at what point you need more accuracy. So for instance, if you are rather mature with your design and then you would start maybe doing a bulbous bow optimization, then of course you would probably replace the surrogate model that has some information about changes in the bulbous bow with the actual CFD tool that you would want to use, so that you have a higher fidelity at the point where you do more specific work. So in that sense, it's there is no clear-cut change from one tool to the next, but you can sort of say along the line of your work, decide when to replace a regression analysis or a surrogate with something better suited for a specific task. And when it comes to the sensitivities, you can actually use the platform very nicely to do this, doing sensitivity studies. you would, for instance, use your optimum design, or the one that you have decided is optimal for you, and do a sensitivity by means of a design of experiment. So you would decide which of the parameters in your model might have the most tangible impact on anything that, if that changes slightly, would have a negative but large effect on your design. And then you would basically run again an additional optimization and synthesis, a sensitivity analysis on the synthesis model to check how sensitive you are. So you can ensure that there is a certain robustness also in the results.
Good. And if I may add, there is of course a certain point in design where you need to go into very fine details. For instance, with the fluid dynamics glasses on, if I may say so, or it could be structural analysis as well. And there you will definitely need to look into exact models rather than surrogates. That's pretty clear. But it's sequential, and it comes very much at the end of each design process. There is probably there's one question which I would like to reply to. Where do towing tanks fit in with the software tools? Do you see a reduction in usage of towing tanks in future with new CFD tools and software? Well, there are two hearts in my chest, of course, working for a model basin, but that is it is clearly so that we are going to shift more work forward in the process and do more numerical analysis during the design process, and that is why we are very much interested in this concept of holistic synthesis design, and want to go into this further also in the future. The role of towing tanks with their experimental facilities will change. That's pretty clear and pretty evident. But right now it looks like we are going to have a need for final confirmations of certain results. For instance, starting with the EEDI verification that is going to keep with the experiment in the tank itself, and we are not going to change this certainly not in the near future, I would say. But so to speak, yes, the answer is clearly we're going to see more CFD in the future. Yeah. Right. Okay. Given the time, we are doing very well, actually. I believe, and I would like to continue that. Can I, Mattia, can I ask you to shift over the controls to Paolo now for his next presentation? Thank you very much, Stefan, for allowing us your insights in the platform work. Paolo will now give a first presentation on an application case. That is after Stefan has shown us how the idea that Apostolos presented has been put to use and formulated in the design platforms. This is now the first presentation that explains how the platform is used for a real practical application case. Thank you very much. Paolo, the floor is yours.
Thank you, Jochen, Apostolos, and Stefan for the presentations, the introduction. So as they have mentioned, we at Kongsberg worked with partners at DNV, Sirena, Bureau Veritas, Sintef to work on design and verification of OSV offshore subsea construction vessel. The work package was divided in 3 phases, where we have phase 1 presented by Stefan, where we connected all the design tools related to the hull design. We have a phase 2 where we designed the power management system. We checked the different alternatives for vessel, for engine size and combinations with battery dimensioning and so on. And we have a phase 3. In phase 2, we also have a life cycle analysis and RAM analysis of that power management system. And we have a phase 3 where we verify in time domain everything that we have designed. This is a rather complex and but a follow-up of how we have done things. So we have in phase 1, this design space though feeds results to post-processing, where we have all the variants analyzed. We have a connection to tools from MPSET and Cosmos from DNV that feeds a RAM analysis in Bula2 and Griff by Sirena and Bura Veritas. And we have the results back to Ålesund at the Kongsberg simulator to verify all the design. So I'll start with phase 1. As Stefan mentioned, these are all batch tools connected to a parametric hull model in cases. First step is that we imported, we checked the hydrostructures of an initial vessel. In this case, it's a baseline design from 2018. We applied transformations of main dimensions and mostly in the bulb design. We applied the parameters that we need and want to change, and we go send outputs to the next step. In this case, it was weight estimations. We have in-house based on all the history of vessels Kongsberg has built. We have calculations and estimations for center of gravity and weight of each accommodation units and equipment and so on. We monitor and we advance to the next one, where we had intact stability. This was checked partially by NAPA and partially in cases features. We checked against IMO constraints of intact stability. We monitor. We create. In this case, if it's a design that doesn't pass IMO, we have a constraint, and all the further connected tools do not execute. It's a unfeasible design. We have motions connected with ShipX and developed by Sintef in Trondheim. We have RAO plots and operability plots in custom plotted in cases to monitor and advance. We have station keeping, then how much power the vessel needs to be kept in place. We get the thrust for each propulsor. In this case, 2 azimuthal aft thrusters, 2 tunnel thrusters, and 1 azimuthal forward thruster. We have then ship flow connected with panel method to estimate and optimize wave resistance. This wave resistance coefficient is fed to a theoretical model tuned to this vessel. We have also pre-calculated the designs and fed a response model, response surface model, a surrogated model to save time in the other evaluations. it was over 500 inside our design space, over 500 designs that I run over a weekend, built the surface model, and now I get wave resistance and PD in basically real time. We have cases feature that based on Kongsberg proposal sizes and designs, we pick the ones that are required for this vessel, for that design variant, the design assembly. And then we had feed those thrust requires, those power requires to Cosmos, which gives initial fuel consumption in a rather simple operational profile. And with this, we can set our design requirements. We had at least 4,500 tons of deadweight capacity. We had at least 175 GM for stability. It must be able to keep in dynamic position in 3.5 meters wave height, 13 knots of economical forward speed, and we have this baseline from 2018 to compare our results. So we start with the robustness check. There was a question from the last presentation where, well, we have a lot of designs, and you need to make sure that all your tools are correctly working, and that your section generation, your panel generation, your geometry generation is robust before you can start relying on all the results. But it was very difficult to identify the trends. But you can see on the right side that those last 4 columns there are fuel consumption, and that you have clusters of fuel consumption, and that's related to the size of the thruster units. So as when you step up on thruster unit size, the whole fuel consumption gets up. We then identified, we tried to organize, instead of doing a SOBO, which is a quasi-random approach, we did a little better organized and checked when stepping up the length and the beam, what happens. And you can see it there on the right side. We had the red bars mean that they don't pass stability. So we always, to a certain length, we need at least some beam to be able to pass the stability. So instead of simulating all these beams, we apply a linear optimization that finds the beam for that length. So now I have a Pareto line of minimal required beam for stability to that length. And then from that graph that was difficult to see, we get much simpler design. So to the right you see a simpler graph, and to the right you get to see the fuel consumption, where 1 means as the baseline project we had. So we can reach about we can get 5% less fuel consumption and CAPEX if we choose a lower length but a bit wider vessel, as you can see the red lines. So from that you could choose a design. In this case was about 90 meters long and 24 meters wide, and we can then get all the thrust values and start feeding the next stage. At this stage we expect to see at least 5% in CAPEX and 6% in fuel consumption. In phase 2 we fed the data that we found in this optimized design from phase 1. We go through a tool developed by Kongsberg, which is MPSET. Parallel to that, we go to Cosmos by DNVGL, and we feed the engine configuration, the power management system to Buddha, and GRIF, where they calculate reliability and maintainability of the vessel. In this phase, we detail the operational profile with more relevant data. Then in MPSET, we select, we have 4 alternative architectures. Alternate current diesel-electric with or with battery or not, and the direct current diesel-electric with batteries or not. Then we have an input list of engine and fuel consumption for each. MPSET has the combination algorithm for the engines, and it started checking what is for that operational profile we started with, what is the engine combination that will give us the lowest fuel consumption and emissions. So it tests, for example, 4 times 2,000 kilowatts, 2 times 2,000 kilowatts, and 2 times 5,000 kilowatts, and so on, in the 4 different architectures, if it's a feasible design. It gives you an output in it's not in a time domain, but almost like that. And fuel consumption, engine RPM, fuel consumption, battery consumption, load at each operational profile task. Gives you for each engine configuration, it gives you the report with the emissions and fuel consumption, and then you can compare all of them. So you see direct current without the battery size having the lowest, adding a battery size, a battery pack gets a bit higher, AC a bit higher, and so on. And you can check all of these, and you also can get them the result. We then fed that lowest fuel consumption configuration to Cosmos. Cosmos checks peak shaving functionality of the battery, preliminary reliability of the vessel due to hot reserve, and tasks like in harbor and having on and off the battery. So, for example, a system without the battery at harbor would consume about 2 tons per day, and they wouldn't have a hot spin reserve, both in case of an engine loss or a switchboard loss, one side of the switchboard loss. So you would have hot reserve in 6 of 16 cases, and when you add the battery, you could have it in 9 cases, and you would get 5% fuel consumption in the overall task. So we decided to proceed with the battery and a DC alternative to the RAM analysis. And battery size should be very close to the engine size, so about 2,000 kilowatts. We have using the battery for peak shaving transient loads that they tested with plus and minus 600 kilowatts, and the lowest fuel consumption was for a battery size, a battery pack that is close to the engine size. In harbor, it has significant fuel consumption reduction when using in mode on and off, and reliability in hot reserve, which is when you can immediately take the load in case of a failure. We proceed to RAM analysis. Buddha was a tool developed within HOLISHIP that can describe the architecture and follow propagation, failure propagation throughout the system. And GRIF is a tool by Buddha Veritas, which takes the input of the failure from Buddha and calculates availability and maintainability. In Buddha, you can build the architecture and have it specify what is a fuel line, what is a cooling line, what is an electric line. You have a component failure, and you can compare. You can check the propagation to which components are affected in case of a failure of a component. And you can also check different architectures. What happens when you connect that component to the other switchboard, for example? Alternative designs of the architecture. Griff then by Bureau Veritas, they take the data, the failure propagation from Buda, simulate it in Griff, and where you can compare the different advantage and disadvantage. It simulates in case of an engine failure, it will turn on the next engine, where you can decide if you proceed with your mission or not. So for example, a transit condition, you see on the left side, the red blocks are components that are online during transit, and then on the right side, the purple are the same components online in Griff. You simulate a switchboard failure on the right side, and you see that you lose, and now you might not be able to complete your mission. But in case a main engine fails, you can start on the next engine if it wasn't if your operational profile allow, and you can proceed with the mission. So they have created what is mission success or mission failed due to transit degraded or transit return capability, and simulated this mission of DP2 operation along the 10 years. Data for equipment reliability, failure rates, critical failure rates, for example. They were taken from sources like OREDA and IEE, applied to our case, and from 365 potential missions, we have started 370, we have completed 324, giving a reliability rate of 88% and 89% availability. It identified that the main generators are the main the main reason for mission failure, and they have then checked what happens when you increase the reliability due to a battery pack, and what if you change your mission your mission criteria if you are able to say that a DP2 can be completed in case even if you lost one engine, which is define how you define your mission success or not. And if you increase the main generator reliability with batteries, for example, you can go from 88% and reach a maximum of 94% of availability, 92% reliability. And if your mission criteria, what is a success or not, it can be discussed, then your reliability is closer to 96%. Failures to consumers are not included. The battery, for example, was not included, which is rather conservative, and which means that the availability and reliability is likely to be higher with a battery pack. And with this power management system, we can start the last phase, which is a power system verification in a time domain simulation in Kongsberg simulator in Ålesund. We've rebuilt the architecture in the simulator, the same architecture we designed in phase 2. We have, like in a Rio vessel, the power management system and the DP interfaces, where you see in real-time loads, angles, heading, deviations. And then you start functional testing. For example, the blackout recover, what happens when you need to suddenly start the generator. And then you follow on the graphs, you follow battery state of charge, the power in each bus, you get the thruster unit per unit, and for example, electric load in the bus in each switchboard. So for this case, what is most relevant is the DP operation. So as with the thruster unit size designed in phase 1 and the same design condition from phase 1 at 30 degrees, all in coincident wind, current, and waves, we check if the vessel is capable of holding its position. So in 800 seconds, this is time domain, wave, current, and wind simulation using the windage areas of the vessel, depending on the size of the vessel designed in phase 1, depending on the windage areas. You see if it is able to keep the heading and the position, and you can follow with the power loads and thrust loads in each thrust unit and power buses. Here you can see it is able to keep position in intact condition, no failures, as expected, as designed. And we started testing failures. In case you lose one generator, so you see to the right, the generator 1 in bus 1 is at 500 seconds is simulated to fail. The loads in the battery and the generator 2 are increased to take over the demand, and heading and position deviation are still under control. Main thruster port side failure, so one thruster unit, main thruster unit failure, same environmental conditions as in phase 1. So you see that the power on bus 1 is reduced at 500 seconds, and bus 2 takes over the load. The main thruster on the starboard side then takes up the load, and the vessel is still able to keep position and deviation. It's all close to 0 degrees head deviation and less than 2 meters position deviation. And then we simulate the worst case failure, which is a full switchboard failure. Same environmental conditions. So the whole bus 1 is turned off at 500 seconds. The bus 1 takes over the load. There is a whole redistribution between of loads from thruster units from one side to the other side of the switchboard. And then we start seeing a little bit more heading deviation, up to 5 degrees, a little bit more than deviation in position, 2 meters, but it is still stable position. So with the design that we have chosen in phase 1, the vessel is able to keep its position in a DP2 operation. And this shows us that the recreation of the power management system and the propulsion in a time domain simulator was successful, and we have designed a vessel to its task without any design measure. That means our simulations, our calculations are rather coherent to each other. So a time domain simulation is coherent to what we have for motion and station keep simulation in phase 1. And if we test in different heading conditions, a 90 degree station condition was also tested, and it does lose position in this case. So here it is on a 30 degrees environmental load condition, and it keeps its position, but at 90 degrees it doesn't, which means that the vessel, the engines and the thrusters are not over dimension, which is also important for, especially for CAPEX costs. In this project, over 3 years, we have achieved many publications, and we do. We are open to share these with you, and any questions you can also contact us. There will be a detailed webinar in 21st of January about phase 1 with Friendship Systems. So you are more than welcome to join and discuss it with us. Thank you very much, and I can take some questions. Otherwise, you can email me anytime. Thank you.
Thank you, Paolo, for this very comprehensive exercise presentation, which showed the practical use of a large number of different software tools within the HOLISHip platform environment, I think this is an exceptional example for the flexibility, usability of the concept idea, and we were able to touch on a number of different aspects, spanning more or less the entire bandwidth of design disciplines for this application case. So far, I think you have been exhaustive, because I can't see any. Come on, there's one question regarding to your presentation. I'll read that. With regard to the GM check, would it be possible to integrate this directly as a constraint during the optimization? That is something that you might be able to answer directly.
Yeah, the GM was a constraint. Maybe it was too fast, but it is. So we calculate the VCG with the weight, and in the next step we do create a constraint of GM and IMO less and fail. Yes, it is a constraint. So the other disciplines in after intact stability, so 4, 5, 6, 7, 8 are not executed, and we jump to the next design variant, the design sibling. It is a constraint, and we in this case we use 1.75 meters, but it is up to us to, because it is somewhat tunable with ballast and different materials in the accommodation and so on. But so it is able to, we are able to change that 1.7 to 2 meters or 1.5 and use it as a constraint. Yes, there is. And so on the right side there, on the last column, you see the red ones are GM constraint failures, where the vessel size doesn't satisfy intact stability. Yes. Thank you.
Thank you very much. I think what is noticeable with Paolo's presentation in that respect is also the fact that although we're speaking in the HOLISHip context about design tools and the holistic design concept and the integration part, but all this is very much in the background of Paolo's presentation. It's there and it's the basis, but what this shows here is that it's actually working quietly in the background, and you can by using this stable platform behind, you can actually look into the most complex design optimization issues you may think of, and a clear step ahead for the future. Now, looking at the time, our next presenter will be George Mermiris from Tritec in Glasgow, and George will speak about their work on the design optimization of a RoPAX ferry. Thank you very much. The floor is yours.
Thank you, Jochen. Hello, everyone. I hope you can see my screen now.
I can see. Yes, thank you.
Thank you. Thank you. So thank you, everyone, for attending. My name is George Mermiris. I'm the general manager of Tritec Marine. We are based in Glasgow. And today I'll take you through the RoPAX design optimization, one of the application cases in the HOLISHIP project. So very briefly, the focus of my presentation will be on the background of what HOLISHIP is about, how we combined aspects, or how we conceived rather the scope of this application case, and how this has a very tangible business element into it. Of course, the technical and the software aspects of the process are very important. I will echo most of the times the previous speakers, and the vernacular I'm going to use is pretty much the same and familiar. So, in the context of a RoPAX vessel, any floating asset for that matter, but in particular of a RoPAX vessel, the element that permeates the whole exercise of the design is that you need to balance a number of factors. It's not just the performance of the asset, of the RoPAX, of the RoRo ferry itself in this particular case, but also the performance of the ferry for a certain commercial output. And this has to happen in a safe and green manner, and it has to satisfy a number of constraints, primarily related to the operation or the area of operation and regulatory framework. So the complexity of the exercise has to be appreciated from the outset. And the importance of the HOLISHIP framework overall as a methodology and as a tool set is exactly there, that it allows the user, the designer in this particular case, to appreciate and combine all these conflicting requirements. So in this project, we had the support of a number of partner organizations spanning between industry and academia, and of course with varying levels, skill sets and qualifications. It was a very interesting exercise for us, and we are very happy to participate and contribute in this work. So a little bit of background. We are talking design, and this by definition is an evolutionary process. So we have established today, or for a good number of years now in Europe, what a RoPAX design or a RoPAX ferry looks like, how it operates, what are the limitations of it. We recently started seeing evolution. So evolution comes in a rather piecemeal approach. So first we have some sort of regulatory framework which drives demand, and in this particular case, the greening operations. So we see adoption of more environmentally friendly fuels. But the whole approach looks like it's not as fast as it could be, or it doesn't grow in parallel to the market demand in terms of what these ferries should be doing for the economy, local or global, for one country or more countries. And of course, at the other end of the spectrum, we see far more evolutionary designs which are out there, concepts which look a lot more futuristic. There is a clear gap between where we are today and where we would like to be. Not that we would like to be futuristic and spaceship looking like, but there is this gap which needs to be filled, and it has to be done in a structured and concise manner. So the evolution of arrangements and performance of Ro-Ro passenger ferries can be definitely happen. Innovation in this context can definitely happen, and it can happen in a concise and consistent manner. And this is the real lesson and output from the HOLISHIP project. So establishing the importance in the economy of the RoPAX ferries for the European economy, like I said, is pretty evident. There is nothing new into it. What we do need to do, though, is to evolve them and grow them alongside the evolution and growth of the market they serve. And to this end, it's very important to be able to explore what we, in a very abstract manner, we call design space. So all the permutations, all the variations of some basic design can be explored, simply because the solution for different markets or different sectors can be found there. But in order to do that, we have to do it in an intelligent way, if you wish. And this way can only happen very early in the design stage, where change of or variation of the design is cheap and easy. So put all this, take all this in context. In this particular application case, we decided to approach it in a twofold manner. One, to design a conventional ferry, RoPAX ferry, the way we know it looks like today, and then to use exactly with the HOLISHIP methodology and toolset, and then use exactly the same methodology and toolset, and design a ferry which will bring a step change into the way the ferry looks. So we started with a certain number of, we call the mature version of it, or the conventional ferry, we call it alpha, and we call the new concept Bravo. So we started with a design specification for a number of passengers, lane meters, propulsion installation, and then we thought that in the Bravo design, we need to evolve this, we need to grow it. So for the same hull envelope, the same geometry, can we actually achieve more passengers? Can we have more lane meters? But at the same time, can we do this in a more environmentally friendly manner without compromising safety? And this is where diesel electric ideas or dual fuel engines with LNG in this particular case came to be. So these are aspects which not only will help in the evolution of the design, but also will will help in the transition between where we are today and where we would like to be. So, stemming from what we know, it's important to appreciate that the approach we have in this in HOLISHIP stems from what we know. But what we know and past experience is not a constraint. So when we explore the design space, we are not limited only to what we know. What we know is the springboard. It's not a limit. So from this point of view, we generate a number of envelopes, and the envelopes correspond to a certain limits. The limits in there, they are not meant to be how to say, to be limiting or constraints. They are there to provide meaningful solution. And this has impact on pretty much every facet of the design: propulsion, operational, and propulsion safety, stability, how green the operation is, how economically feasible or unfeasible it can be, the concept. So once we have the envelope, we also need to look after the internal arrangement. And this is where the real challenge is most of the times. So where exactly we place the crew, or the passengers and the cars and the trucks. Every one of these aspects has a financial implication. In addition, every space has to be created, defined, both based on what we know from the past, what rules we have to satisfy, but also how we want to evolve it. And this is one of the strong elements of the HOLISHIP platform or methodology overall, is that it does allow imagination and creativity to kick in. For example, in this particular case, we see how the introduction of one extra bulkhead in the arrangement can change, and I would attract your attention down here, can change as a function of lane meters or of length between perpendiculars. So by introducing just one new bulkhead, we can immediately see how transportation capacity in terms of passengers and lane meters changes. And this is a very important part of the whole approach. Powering is an integral part, obviously, of every floating asset, especially a ferry. And the other element that kicks in here is that all of a sudden we need to start connecting fuel consumption, obviously, with financial performance or with a given geometry. So obviously we are not talking for continuous variables like the length of a vessel. We are talking for variables where we have one or two main engines, three main engines, one, two, or three auxiliary generators. And all these are assessed for certain configurations of geometry based on a number of combinations. So what is the objective? Obviously minimize fuel consumption. What is the constraint? The constraint: minimum and maximum operational loads, or the geometry. How much space do you have available on board to accommodate so many engines? Structural design is always an issue. In its own, it has a certain level of complexity, pretty much quite separate from the rest, simply because you have to identify and you have to tackle so many elements which constitute the structure of the vessel. In this particular case, we used the BV rules to calculate primary and secondary structure of the vessel, the topology, frame spacing, all follows the initial parametric model. And of course, the objective was to minimize the still weight without failing to comply rather with structural rules. Weight, always a very critical element for any floating asset, and also for a passenger ferry especially. And again, it taps into a number of aspects concerning machinery, outfitting, and of course, still weight. And these elements are based not only on, or this information is not only coming from class rules or past projects or past designs, existing designs, but also from data from manufacturers. Remember, the underlying assumption is that we are not only using, or we are not only meant to use what machinery and equipment is conventionally deployed, but also to make use of state-of-the-art machinery for the future. Passenger ships and stability go hand in hand. There is little doubt about it. Every regulation that needs to be satisfied should be satisfied, be that of intact or damaged stability. The element that this slide stresses is that the safety facet of the floating asset of the RoPAX ferry is not something that is overlooked. So it's not just the performance of it as an engineering artifact, it's not just its performance as a financial asset, but also its safety and of course its green operation is there. Response surfaces or surrogate models, as the term goes, are inevitably used. We are dealing with a complex asset. You have to produce surrogate models, and depending on how much data, time, what software tools you have at your availability, the complexity and resolution of the surrogate models will change. The important fact is that unless you use these models, you cannot engage in assessing large numbers of design permutations. By large numbers, and large numbers means the larger rather the number, the better the design space is explored. And from this point of view, it's that important to utilize the kinds of surrogate models that fit for the particular exercise. It's also important to say that surrogate models are not first principle tools. Yeah. So in due time, and when the next phase of the design is triggered, more detailed analysis can always be done in different ways. Right now, we are still in the exploration phase. So in our case, design of experiments was set up between cases and Naval, and some 3,000 design points were generated. Overall, the alpha design came to be the configuration you see there. It's a conventional design, Ferry, the way it should be, or the way you would expect it to look today, full compliance with applicable regulatory framework, at least for the phase or the stage of development that we took this design forward. And here's when the exercise started becoming interesting. So at this point in time, our task was to utilize exactly the same tool set and see how we can evolve. And by evolution, we set ourselves the target to ditch the conventional propulsion machinery and use diesel electric. Why? Simply because the diesel electric installation by definition allows a lot more flexibility to be placed on board. But at the same time, we also acknowledge the fact that LNG becomes a transition fuel, or it's the fuel for at least a few years to follow from today. So put two and two together, and immediately you see that the need to create fuel tanks with cryogenic medium in it, and the availability or the potential of diesel electric installation and the flexibility it has to be placed in a certain arrangement, then some very interesting results are defined. Now, in this particular case, you see how the LNG tanks can move in different places versus the location of the engine room. So combine this with body propulsion, with all the benefits that come with it in terms of maneuverability, and then all of a sudden we are having a concept which potentially can beat, or it's potentially better than a conventional ferry today. But the very interesting part is that the same evolution, or this evolution rather, was achieved based on the same platform, the same toolset, with the sole difference is the adoption of more state-of-the-art equipment. So you see up here, up until a certain point, the envelope remains the same. And then you see permutations and variations start to happen. I should apologize in advance for I don't have all the figures because of the timing in this work. Not all the data was post-processed on time for this presentation. Like Jochen mentioned at the beginning, the project will finish at the end of the year, and I think we will be one of the last ones to conclude. So I do apologize for this. But the real message here is that the two designs are there and they have been achieved. So in conclusion, the RoPAX Ferry as a specific vessel type has the potential to evolve. As an engineering community, working in academia or in the industry, our task is to generate arguments. And we generate arguments by using concise methodologies, well-established mathematical models, and very well implemented software techniques where we can definitely produce numerical arguments and demonstrate that designs of the future are really achievable with today's means. This is not blue sky thinking anymore. This is here now. So all we have to do is just to grasp the opportunity and make the best out of it. Thank you very much.
Thank you, George, for this elaboration, which clearly had a rather different focus compared with the Kongsberg presentation, looking into different design disciplines. But the more it emphasizes the possibility to use the HOLISHIP platforms in a way that is very, very flexible and allows to address totally different aspects as well. I encourage you all to ask questions if you have any. In the meantime, I would just like to comment a little bit on George's excuse for the progress. That is, there is no way of criticizing that. There's a little bit of project history behind that because he and Tritec became in charge of the RoPAX application case only rather late in the project. We originally had another partner, but they had to withdraw due to business problems. And I was just looking at the list of participants, and I'm very happy to see that some of our former colleagues from previous Uljanik shipyard are still in the picture, and they follow us on during this presentation as well. So far, there's probably one thing I would like to ask you, George, because we are, of course, very much interested in the future of the entire HOLISHIP process. Are you any plans, or do you have any plans how you would use those results for new projects now? The Alpha and Bravo certainly being more or less role models, and this is not a concrete new ship design, but do you plan to transfer these ideas into something that we might see on the water in a couple of years from now?
Absolutely. The whole idea here is that this is not an R&D project only. There is a very tangible and measurable commercial interest for us, and what you will see in the water in the next, hopefully starting next year, is not necessarily passenger vessels, but the same methodologies, the same tools will be applied for the design of small-scale LNG carriers. I would encourage everyone to have a look in our website. There will be, keep an eye on it, there will be news coming out soon.
Very good, thank you. So in view of this and the time, we are still very good, I must say. I would like to ask Mattia to prepare for our final presenter. Markus Jokinen from Elomatic, who's going to speak about yet another totally different design exercise for a electric driven double-ended ferry. And Markus is presenting especially the intelligent general arrangement which Elomatic have produced in the context of the HOLISHIP project. Thank you.
Oh, hello, my name is Markus Jokinen and I represent Elomatic in this presentation. I will introduce you the Intelligent General Arrangement platform and its application case study double-ended ferry that we developed during the HOLISHIP project. First, I'm going to tell something about myself. So I work currently as a project engineer in Elomatic. I started in Elomatic since 2016 when I started to do my master thesis. Its subject was basically how to improve the general arrangement design process at concept phase. So the subject is very near the HOLISHIP project itself. But that's about me, and let's go on to the actual double-ended ferry case and intelligent general arrangement platform. So the intelligent general arrangement platform was developed. It is a design and optimization platform developed in HOLISHIP project. This double-ended ferry itself is an environmentally friendly battery-driven vessel that operates in Finnish archipelago in northern Europe at Baltic Sea. So you can get the picture where the operation area is from this slide here. Our double-ended ferry is an ice-strengthened vessel according to Finnish-Swedish ice class rules, which is capable of operating at winter times. So it has ice breaking capability. So what were the main targets of the HOLISHIP project then? We have basically three objectives. The first one was to generate a parametric 3D ship model and general arrangement that can be easily modified after initial design. The second objective was to optimize several objectives like resistance, propeller load balance, steel weight by optimizing ice belt design. And our main goal was to optimize net present value, which basically describes the profitability of investment. In addition, we made an automated stability analysis to ensure that all intact and damage stability regulations are complied with. So that was the second objective. And the third one is that because battery-driven vessels are relatively new, we studied their performance against the traditional diesel generator set option and hybrid version, where we have both batteries as a main energy source and diesel generator sets as an auxiliary source. And here is the intelligent general arrangement design and optimization platform, also known as ICA platform, that we developed during the HOLISHIP project. If I'll say something about this, that we use this CADmatic model, CADmatic software to model the 3D ship model and general arrangement using a hull shape, a parametric hull shape that was generated in cases. And the structural assessment was done in Bureau Veritas Mars midship analysis tool using the structural data from the 3D model of Cadmatic. In the lower part, you can see the Bureau Veritas CCAT tool, where we basically dimensioned the batteries and simulated their performance against these other mentioned options, hybrid and diesel generator set. On the right part, you can see that Fresco Plus and XNavis CFD tools were used in resistance and propulsion analysis of the vessel. We had a nice new feature about stability, because Hochschule Bremen established an automated stability analysis procedure between cases and Napa. So I'm going to talk this later more. And on the lower left corner is that you can see that we calculated in cases the net present value based on capital expenditure, it's mainly construction costs, and based on OPEX, so for example, salary and the power consumption based on resistance. So net present value was our main target to optimize in this project. Let's go deeper, the link between cases and Cadmatic itself. So on the upper left corner, you can see the parametric hull surface that was generated in cases. And when the initial hull shape was generated, it was transferred to Cadmatic, where naval architects add structures to the model and some outfitting items. You can see some stairs and doors, and there are inside the hull also the batteries as a 3D outfitting items. These decks and bulkheads in Cadmatic are modeled as a parametric, so cases can modify both the hull shape and these bulkhead positions in an automated batch mode. And when we modeled the Cadmatic model, the steel weight and light ship weight is transferred in XML format back to cases, where it is used in hydrostatistics, stability analysis, and CFD analysis. So then the optimization loop starts after initial design. So this is the Cadmatic cases link in a nutshell. One new tool that we developed was an ice belt optimization tool, which is basically a case script that will automatically generate ice belt area and ice strengthening members for the cases parametric hull model. And based on the ice belt area, length of the profile type and material type, the script generates added steel weight comparison data that you can see in this slide here. So the obtained data shows the weights for two framing systems, transverse and longitudinal framing systems for different spacings. For example, in our double-ended Ferry, the standard spacing was 700 millimeters. So we see that the lowest weight is obtained using transverse framing system with 350 millimeter spacing. So the optimal ice belt structure is to have ice frames at every half frame. This was a good to know, especially because the ice belt weighs quite a lot in respect of the total steel weight of the vessel. What this ice belt optimization tool also does is to provide the weights for different ice classes according to Finnish-Swedish ice class rules. And here you can see the results from ice class 1A, which was the double-ended Ferry's ice class. Let's move on to this stability part. So as I mentioned, Hochschule Bremen established an automated stability analysis link between cases and NAPA. So from cases, the hull form, wind profile, and other data is transferred to NAPA, where the compartmentation and stability analysis is done. And basically, the intact stability was done according to ES code 2008, and deterministic damage stability was done according to EU directive of the European Parliament and the Council of Safety Rules and Standards for passenger ships. So this double-ended Ferry was non-SOLAS ship, so it has some different stability requirements regarding to normal SOLAS rules. And here you can see the result from the stability analysis itself. So on this figure you can see the permissible GG for laden ship to comply with all intact and damage stability criteria. For example, if we have depth of 5 meters, we know that we can have GG up to 6.5 meters. And this means basically that the total GG value can be 1.5 meter higher than the depth of the vessel, so mainly the main deck, which is the car deck in our case. This is good to know because, of course, on the car deck we have cars and trucks, so the GG will be higher, so we need some reserve buoyancy. So this is a very good tool to see what are the acceptable configurations and what are not. This stability tool here. One mention is that we noticed that generally it can be stated that the double-ended Ferry has an hull form which is beneficial in case of damages, and because we have sharp V-shaped in our vessel with hull wing extensions at guard deck level to increase guard line areas. So the submergence in case of damage is very limited. So this was a very good vessel in respect of damage stability. And here we move on to the resistance and propulsion chapter in my presentation. So CFD analysis for resistance and required power was performed by HSVA, and you can see that we wanted to get the resistance and required power for different lengths and beams of the vessel, and for that we changed the beam length of the vessel, and then we changed the drafts and trims of the vessel and speeds, so we get the results for several parameters as shown here. And this response surface matter shown in the upper right corner, where we have this length and beam as a parameters and resistance as a response, we used in cases to calculate the electricity consumption and the operational cost for the vessel. On the lower side, you can see the analyzed results from propulsion analysis. It's basically at the you can see that this pod diameter was 1.7 meter, and we tried to optimize their positions and the load balance. And according to propulsion analysis, the optimal position, optimal load balance for the propellers was to use only aft pods, but according to Finnish ice class regulations, it was recommended to use 4 pods instead of 2, because the power demand would have been unnecessarily high if only using 2 pods. So, for example, if we had 4 pods, the required power demanded by Finnish ice class regulations was 1.8 megawatts for the vessel with overall length of 121 meters and beam of 19.6 meters. For 2-pod solution, the demand was over 2.1 megawatts, so the increase was even 22%. So that's why we ended up to use 4 pods instead of 2. And based on, of course, the hull shape was limiting the factor to use only 2 pods. This is the battery study part now, and basically the Bureau Veritas dimensioned the batteries and simulated the performance of batteries in our vessel, and we compared these batteries against these other options that I mentioned before. Bureau Veritas used their CCAT tool, which is basically a tool to simulate complex ship energy systems. So the simulations basically starts by defining the operational profile of the vessel. This operational profile contains maneuvering stage, acceleration stage, cruising stage, and the stage where the ship recharges its batteries at the port. So in our case, the cruising speed of the vessel was 13 to 14 knots, and the round trip was 10 nautical miles. So the half trip between port A and port B was 5 nautical miles. And from the operational profile, we get the power consumption at each point. So we could, based on this information, simulate the state of charge levels at each point. And you can see the results for the summer condition and winter condition in this slide here. Those spikes at 5 hours, 10 hours, and 15 hours are caused by lunch breaks and the crew changes when the ship has more time to charge its batteries. And those smaller spikes are, of course, caused by the charging of the vessel, because this double-ended ferry stays at each port 10 minutes where it recharges its batteries and loads and unloads its cars. And this it was we found the interesting fact that classification society says that we have to have shock level always at least 50%. So based on this information, we dimensioned the batteries based on winter scenario, and the resulted battery capacity was 9.5 megawatt hours, as you can see in this slide here. Those in hybrid and diesel generator set options, the dimensioning was based on the similar manner. So so I'm not going deeper on that in this presentation. Here is some interesting results that we obtained from the battery study. So we can see that energy demand by fully electric vessel with batteries has much lower energy demand than fuel diesel, because batteries can utilize almost 90% of the energy provided, whereas this fuel diesel can only use up to 40 or 50% of the energy it can take. And so battery vessel is very good in this respect. On the right side, you can see the gas emissions between hybrid vessel and diesel option only at the operational stage. So with this figure doesn't show the emissions during the manufacturing of batteries, but it would be, of course, very important thing to check the life cycle emissions as well. And this gas emissions table only shows the winter comparison, because we assumed that in hybrid vessel the batteries will be the main source of energy, and during the summertime it only uses batteries. But in the winter time, where we have ice resistance, we need to use also diesel generator sets. So this result is only for winter situation here, and you can see that the hybrid wins in both emissions, as you can see here. And one interesting fact was to, of course, investigate how much weight and volume these systems takes on board. So you can see that batteries has highest weight and highest volume, because their volumetric and gravimetric densities are much lower than internal combustions generally has. And this bunkering of 7 per 7 days is based on the fact that in our calculations the vessel would use 45 cubic meters of oil per week, and we could have a truck with capacity of 50 cubic meters of oil filling the onshore oil tanks, where once per week, where the ship can fill its own tanks. So it was a realistic scenario to use this once per week bunkering. And now we are heading to the final slide of the presentation, where you can see in this table the main particulars: length overall, breadth overall, etc. And in the second column you can see the range where the optimization in cases went, and you can see, for example, that length overall could be up to 129.9 meters, because according to regulations we would need for passenger ships to have an additional helicopter landing area if we have higher lengths than 130 meters. So it was interesting fact to know also for us, and also limited the optimization area, design space where we optimized. The beam of the vessel could vary between 16.7 meters to 22 meters, and it mainly depends on the number of lanes on board. So we could have from 6 to 8 lanes either on one deck or at the Tritec, and the constraint for us was to have at least 150 cars on the design. So based on this information and constraint, we started the optimization, and in this third column you can see the final version where we ended up. So this version provided the optimal net present value that I mentioned before. So we can see that in the final design we have length overall of 121 meters, and breadth overall is 19.2 meters. And as a general arrangement layout, we have on deck 1 we have batteries and propulsion. On deck 2 we have cars and trucks. So it's the deck 2 is the car deck. On deck 3 we have assembly stations, for example, emergency assembly stations, including live rafts. On deck 4 we have passenger launch, and the deck 5 is the wheelhouse deck. That's it basically. We have this net present value seems to be somewhat very low for 25 years of life cycle, but we have to notice that these double-ended ferries usually run by taxpayers' money. So basically we are satisfied when the net present value is positive, and it was in this scenario as well. And finally, I would like to thank all the HOLISHIP partners involved to this project. It was an interesting project to go through. Thanks.
Thank you, Markus. This is an example that HOLISHIP can also or allows to do two other address two other important lines. First, we can go into ice, and secondly, we go green with an electric propulsion unit, which is of course quite interesting and important also, especially for today's requirements, and not only today's but certainly tomorrow's requirements with respect to emission control and so on. We are reaching the end of our workshop. I would like to thank all the speakers for being here. I would like to thank all of you who attended for your interest in the project. And we now have a short round of 1 or 2 minutes for the speakers to say 1 or 2 final words, if you like. Is there anything that you would like to add? Let's start with Stefan.
Yeah, also thanks a lot from my side. I think with the 3 very elaborate application cases, you could get an appreciation of how flexible the platform has become. I want to point out again that our intention was not to replace any tools in the market or to sort of say come up with a super system that would solve all problems, but rather to propose an approach that is flexible and that can be accommodated in practically any environment. And I think the diversity of the application cases has shown that, and hopefully, but by what I explained, you have understood how the integration is done.
Thank you. Apostolos, do you want to add something?
Yeah, well, just closing 2 things. The first one, for me personally, I was thinking about this project many years ago when I started working on this with my students and associates. And now seeing the outcome, it is of course beyond any expectation. as it produced tangible results, and I think the future is there. But before closing, I'd like Jochen to thank you personally, not only for moderating today this webinar, but also for the close collaboration we had over the past 4 years in this project. And actually, our collaboration started 6 years ago when we first discussed this project between us. Thank you very much, and I hope you continue like that at HSVA with HOLISHIP. Thank you.
Thank you, Apostolos. We'll see what the future will hold. I will certainly try to keep myself into this sort of business. I can only return these compliments, because for me it was a real pleasure to be able to work with you, as well as with all the other partners on this large and interesting project. George, do you want to add something?
I will probably echo everyone else behind me and the speakers. It's been a success. This project is meant to make waves in literal sense. All I could say is that I would encourage both practicing colleagues and engineers, as well as new engineers, to delve into these approaches. Get familiar with these methodologies and the software, because this is really where the future is. Thank you.
Thank you. Markus?
Yeah, I would like to say that this was very interesting and challenging project, at least for me, and it was quite extensive when you consider that it took almost 5 or 6 years to accomplish. So, and yeah, I would again like to thank all participants. It was a very nice job.
Thank you very much. Yeah. So that leaves it to me to say 2 final words, probably. I hope that all of you enjoyed today's workshop, and that the presentations shown gave you an idea of the flexibility and versatility of the holistic synthesis concept and its implementation in the HOLISHIP project. The examples that we have seen today address a large number of disciplines, but also tools. Stefan, in his second presentation, had a list of tools that have been used and integrated, and by now these are more than 40. And this is clearly our way forward, which we would like to follow also in the future. And in that respect, we find the idea of the common marketplace has a quite old-fashioned and also novel notion these days, I should say. Find this idea very interesting, a concept that we wish to pursue further in the coming years. And if this is also to interest to some of you in one way or another, you have the opportunity to indicate that in the little questionnaire that that will be shown when you leave the workshop. Get in touch with us if you're interested, and we can continue how we can discuss how we will pursue this further in the coming year, especially. Once more, we are very, very grateful to the European Commission for funding HOLISHIP and giving us the opportunity to develop all these interesting concepts and ideas and tools. And I would like, finally, one more time, I would like to thank you for your interest in the workshop. And I'm a little sorry for not being able to host a big physical workshop. That would have been a great smashing thing to have, but it will also be a smashing thing for Corona, I believe, and therefore we're not going to hold that. We hope that we will have other opportunities in the next year, with all the vaccine being available and hopefully soon distributed, so that that hopefully by summer next year we will be able to have new ideas and the traditional conference workshop sort of thing re-established, and then have another opportunity to discuss with all of you HOLISHIP ideas further in the next year. Thanks very much to all of you, and that is now from my side the end of this presentation. Thank you very much for your interest.
Thank you.
Take care.
Thank
Bye
you.
bye.
Thank you.
Bye.
Bye.